great thing. Okay. Now there's another extremely important relation for our electrical field. Okay, so have you studied Helmholtz's theorem in your first course? No? So what Helmholtz's theorem states is that if you give me the divergence of a vector field and the curl of a vector field, I know the vector field modulo and a constant. Okay, but I mean, I'm not going to insist on it too much, but let's kind of take a step back now and come back to the other possibility. We're going to talk about the divergence of E and Gauss's law. Change the color again. Okay. Divergence of E and then Gauss. So what's our picture? Our picture of the electrical field, we have a certain source charge here, and our electrical field is really a kind of series of arrows coming out. Yeah, like this. And if we imagine a kind of situation where we define some kind of integration surface, in this case, as you can obviously from the drawing, a kind of sphere around the object, we can imagine the field as having little arrows piercing through the surface. And if we were to imagine that the electrical field was this kind of fluid constantly flowing out of this, just to get an abstraction, there would be a question of a flux of that stuff through the surface that we have. Okay, so the kind of thing that we want to compute is what this flux looks like. Okay, so flux of E through a surface. Okay, and what we're going to do is we're going to keep it easy. We're going to consider a field of a single charge at 0. And we're going to have a little spherical shell around it. So the surface is a spherical shell centered on it. Centered on 0. Okay, so then we compute the integral over the closed surface. It's now a closed surface. Therefore, the little sign in the integral here tells you it's closed surface integral dA dot E on this. And what would that be? Well, let me use spherical coordinates. 1 over 4 pi epsilon 0. And then what do? I will do an integral over this spherical shell at a certain radius r. Here I will say that the radius of this is r. Okay. And this is then on this surface here. So you know you remember your spherical integral things. So here let's just see what this is. So the my elements for the yeah. So maybe I can do a little drawing to help you out. So I've got my 0 here. I've got my certain radius here, and then I've got, you remember, my angle theta. I've got my angle phi going this way, right? And then I have a little differential surface element here, okay, which goes out in the r hat direction. And the size of that thing, you see, this side here is just, I just do r d theta. And this size here is r with the sine of theta times d phi. I said I would use the curly phi to always do the thing to differentiate it from the potential later. Okay, so I've got my spherical coordinates. Okay, I've got my sphere circumscribed by the whole set of coordinates. And I have a little differential surface element here whose size is r d theta by, there's an r d phi, but because I'm tilted, there's a sine theta, right? Because here, if I turn theta, there's no size. But here, if I turn, here, if I turn phi, there's no size. Here, if I turn phi, there's size, right? Okay, so that's the little differential element. So dA in this case, right, is equal to r squared sine theta with d theta d phi. And now I'm just integrating over theta from 0 to pi and phi from 0 to pi. Yeah. But let's just have the whole thing here. So I've got this d theta d phi, but then I've got all these dependencies put in there. So first of all, I've got the q over r squared coming from the electrical field evaluated on the surface. And then I've got the sine theta with r squared with d theta d phi already in here. Okay, so you see it's quite nice. The r squares go away. The integral over d theta sine theta just gives me, you know, just minus cos theta, which I evaluate between the two, gives me a factor of 2. Integral over phi gives me a factor of 2 pi, which gives me 4 pi in the end. And what that gives me in the end is just q divided by epsilon 0, nothing else. Okay? So that's the observation. And now the idea is that if I have an arbitrary distribution of charges, for each charge, I'm going to be able to do this reasoning here. And if I was to change the shape of integration, I would not change the value of the integral, right? Because by deforming the surface, I also change the flux going through that thing. And you can convince yourself that this is true by kind of thinking, indeed, what happens. Let's say you've got the point source, and all these bullets explode out uniformly. And you have a protocol for measuring the flow of bullets through a surface. Then what kind of flow would you get if your surface was beautifully spherical, beautifully machined, perfectly spherical, versus your colleague's surface, which is just a completely mashed up potato, but which still encloses the whole thing? You would both measure exactly the same flux per unit of time of things going through, right? Because if your shape is a bit more too much, then there's much more surface, but the same flux, because the projection of the flux onto the surface is independent of the shape of it. And therefore, so since this holds for any distribution of charges in the interior, and for any chosen shape, of the surface what we get is Gauss's law. Gauss's, you see, it's like an annoying thing to do. Gauss's law, which tells you that the surface integral over a closed surface of your electrical field dotted into the differential surface element of your surface is simply proportional to the total charge enclosed by your surface divided by this epsilon zero that we have. Okay? And this equation has labeled GL, Gauss law, and then sub I for integral form. Okay, and again, it's absolutely fully deserves. This one deserves like multiple green rectangles. This is the most green rectangular equation you will meet in a long time. Okay. So again, you've seen this before, at least I hope. And because it's true for all S, we can glorify it to, again, its more differential form, which means that the we can use the divergence theorem. Divergence theorem tells us that the closed integral, dA of this thing, becomes, over a surface here, becomes a volume integral of the divergence of the vector field. Okay? So this whole thing by Gauss's law is just Q enclosed over epsilon zero, which I can also rewrite as the integral over the volume of the charge density rho. Okay? And therefore, we obtain the differential form of Gauss's law, which is that the divergence of E at a certain point, here I'm actually going to write the coordinates to be clear, is equal to the density of charge in that region divided by epsilon zero. Okay, and this is Gauss's law in differential form. D. Green rectangle. I should move it up a bit. Okay. Again, familiar material that you've used before, hopefully. Okay. But here, of course, there are many abstractions. First of all, the abstraction of the electric field. But here also, there's the abstraction of the local density of charge. And we said things in the first lecture which are completely counter to this, because we said that charge came in discrete units. Therefore, how can I have differentiability if I'm always a multiple of a fundamental unit? The limit does not exist. Yeah, all the epsilon delta reasonings you've done in your analysis courses, or you haven't done in your analysis courses, they don't hold for charge, because I can't take the limit of my epsilon delta going to zero. At some point, my epsilon hits, the charge of the electron. However, if we are focusing on more macroscopic properties involving great numbers of these things, then we can approximate the real physical charge distribution by a smooth function. But it is an imperfect approximation, However, if you want to probe the imperfection of the approximation, you have to do some pretty advanced experiments. Most of the stuff that you're interested in, it still holds. Okay? So if you want, in that sense, the integral form of Gauss's law is more robust, because this one works absolutely fine. Yeah, even with quantum stuff, whatever, that absolutely works. But the differential form like this, well, you got to have a good interpretation for what this rho is. And then, you know, for the mathematicians among you, then it's not that it's a real smooth continuous function, it's just a distribution, like a bunch of Dirac delta functions flying around. But then it still holds. Okay, but that you don't have to worry about at this stage. Okay, so I hope this is all like familiar stuff for you. And now, so why is this useful? What's the utility? It's to get the electric field in symmetric situations. Okay, and here I presume that you have done that, you know, day in, day out. Am I correct? So like if we do the so example. So E outside a uniformly charged sphere. Of radius r. So what do you do? Well, we compute the closed integral, the A of E, on a certain surface here that is to our choosing. So let's say first of all that S is a ball of radius little r, which is bigger than big R. Okay, so what do we have? We're computing the surface integral of the flux of E through that ball, which is now bigger than the sphere containing the charge. Okay, so what do we have? Well, it's completely symmetric. So irrespective of how I rotate my sphere, it's going to give me the same answer. So if I actually compute this integral, what it gives me is just the value of the field in the radial direction times the surface of the ball, right? So what do I get? So the integral is just then equal to just 4 pi r squared times the value of the field in the radial direction outside. This means the radial component. Okay, and what do I know? I know that the total Q enclosed is just going to be the total charge in there. And here I should tell you what the total charge is. So total charge here is Q. So the Q enclosed is just Q. And you see that immediately tells you that the E that you measure outside is just 1 over 4 pi epsilon 0. It's in the radial direction r hat. It has a 1 over r square dependence and is proportional to Q. That's it. Okay. So superbly economical, works for spherical things very well with spherical coordinates, works with cylindrical things very well with, you guessed it, cylindrical coordinates, works with planes very well with either Cartesian coordinates or, you know, again, cylindrical coordinates, doesn't matter. You can use this thing quite a lot. So maybe if needed, or maybe, you know, so check. Are you able? Oh, no. It seems like my application crashed at the very last thing, but let's see if we can recover. Well, okay, I'll try to recover it. But I was going to tell you, check that you can use the reasonings with Gauss's formula to recover the fields in the other two examples that there are on this page with Gauss's law. Just search for Gauss's law, and then you'll find that page. There are 3 examples in there. One spherically symmetric, which we just did. One cylindrically symmetric, which you should check that you're able to do, and one which actually 2 which involve these infinite planes, which you should also be able to do using this Gaussian pillbox. So this is again stuff that you should have done in your previous course. So I'm just going to let you revise that. And if you don't feel comfortable with these things, then please, you know, make sure that you do become comfortable again with these things again, because these are like we're warming up still, right?